55.5 molar. This means that in a liter of water, there are 33 trillion molecules of water. And since our bodies and cells are largely water, we need to take this water into account when we're thinking about how molecules are working. And so water can kind of be like taken for granted, but really it's fundamental to understanding how everything is playing out. All of these biochemical reactions are playing out in our body, and it plays this key role in kind of like helping explain how molecules bond and how even how enzymes work, even though these things have the water, like you would think, has like nothing to do with it, right? Wrong. So let's talk about water and this crazy molarity and things like the entropy effect that you get from binding things in water and releasing the ordered water molecules, and all of this really cool stuff that we can kind of tend to overlook.
So as I said, water has a molarity of about 55.5 molar at like room temperature. And so what does this mean? Well, basically molarity, we represent it with the capital M, and it is a unit of concentrations. We're saying like how many molecules in a certain amount of liquid. And with molarity, a 1 molar solution has 1 mole's worth of molecules in a liter. And so what is a mole? It's kind of like the biochemist dozen, instead of a dozen, like where you have like a dozen stand for like 12 things, we have a mole stand for 6 times 10 to the 23rd things. So that's Avogadro's number. And it's this really, really big number. And so just to put it in a little perspective, if you were to order a mole's worth of bagels, you would get enough bagels for about 86 trillion bagels per person in the human population. So yeah, so pretty big numbers, but we're dealing with really, really tiny molecules. And so these big numbers make sense. But normally we don't have like this many, like water's like crazy that has like a 55.5 molar concentration, and we'll get to where that comes from in a minute. But typically we're dealing with things in the like submolar. If we're dealing like when we're talking about proteins and cells and that sort of thing, we're typically talking about like the nanomolar range, so like billionths of a mole, which is still really, really big numbers, but not nearly as big as we're talking with water. And so there's way, way more water than there is like anything else. And so like in terms of how much water there is per one thing of anything else, there's way, way more water. And so everything always has to kind of compete with water. And this can be a hard competition because, as we'll see, water has these properties that makes it like a really good solvent, so really good at like dissolving things. And also water really likes to hang out with itself and not so much with some other things. And this is going to have this thing called the hydrophobic effect that we'll talk about. But first, let's get into where does that concentration of water come from? Well, just we can calculate the molarity of anything if we know some things about like its density, its molar mass, that sort of thing. So the molar mass is basically saying how much does 1 mole's worth weigh? And so as we said, a mole is 6.02 times 10 to the 23rd molecules of something, and we're saying, okay, so how much does that weigh? And so if you have water has this molar mass of 18.015 grams per mole, and at room temperature, it has a density of 1 kilogram per liter. And so basically, if you do a little dimensional analysis, factor conversion, unit conversion, there's a bunch of different terms for it. I have more on this if you're interested, but it's a super helpful thing. You kind of just like cancel out the things that cancel out, and it helps, this graphical form helps you like make sure that you cancel everything out and divide or multiply with the right things in order that you cancel everything out to get your answer. And here we get 55.5 moles per liter. And so this is the molarity of water, and this is at room temperature. So there's also this concept called molality. And the basic idea is that if you have a solution, like if you increase the temperature, the molecules, so basically the only difference between like a liquid, a gas, and a solid is how much energy the molecules have. And so the water molecules are going to be sticky to one another. And so if they don't have enough energy to break free from one another, then you have like a solid, so you have like ice. If you have more energy, they can slide past each other, you get a liquid. And if they have a lot of energy, then they can move far apart from each other and form a gas. But even if it's not a gas yet, it doesn't have enough energy to fully break free. If you give a liquid more energy, so you heat it up, the water molecules can move farther apart. And so when you increase the temperature, you're adding heat, you're adding energy, the molecules move farther apart, but the number of the molecules doesn't change, and the weight is going to stay the same. So if you were to use your density, so if you were to use this calculation where we incorporated the density in getting this molarity, and this was the density was at room temperature. But if you increase the temperature, your density is going to go down, and so that would change your molarity. So molality can take this into account, and so molality is moles of your solute per kilogram of solvent. So here we're going moles per kilogram instead of moles per liter. So the molarity is going to change with the temperature, because so you can imagine that if your temperature is increasing, your density is going to decrease. If this is decreasing, you're going to get a lower molarity. But the molality is going to stay constant, and so sometimes you'll see molality used instead. Speaking of the states of water and this, like how far apart things are, water's weird in that when it freezes, it actually, most things when they freeze, they get like more dense, they get like more compact. But with water, it actually expands. And so this can happen like in pipes, which is why people sometimes add like antifreeze. And it can happen when we're trying to freeze our proteins in the lab, which is why we can add like cryoprotectants like glycerol or ethylene glycol, propylene glycol, various things, especially when we're like doing extracrystallization and stuff. More on that in other posts. But the reason why it's doing this is because water likes to form what are called hydrogen bonds. And these require, to be optimal, they have these preferred angles. And these preferred angles are going to make water want to freeze in this expanding conformation, and this is why ice expands. So what are these hydrogen bonds? Hydrogen bonds are a strong form of a weak bond. So they're not really bonds per se, they're more like strong partial charge attractions. And so when you look at water, water is what we call polar. It's like this classic example of a polar molecule. It's like the queen of polarity. So basically, in water, as in all molecules, the atoms, so like the oxygens and hydrogens in water, are being held together by sharing pairs of electrons. And so each atom has these subatomic particles. There's these positively charged protons and these neutral neutrons in this dense central nucleus. And then they're surrounded by a whizzing cloud of negatively charged electrons. And they share pairs of these electrons to form bonds, but they don't always share fairly. And some atoms are they hog the electrons when they're sharing pairs with others atoms. And so when the oxygen and hydrogen are sharing electrons, then the oxygen is going to pull the electron density away from the hydrogens. So they're kind of shifting where the electrons like to hang out in their shared cloud. And so the oxygen is going to be partly negative and the hydrogens are going to be partly positive, because it's, even though the molecule is neutral overall because they have an equal number of protons and electrons, the protons are staying put, but the electrons can be shifting. And so the oxygens are going to be partly negative, the hydrogens partly positive. And when you have opposite charges, well, opposite charges attract one another. And so these can form these like partial charge attractions with one another, and they can form what we call hydrogen bonds. And so we just call it basically a hydrogen bond is where you have a lone pair, so a non-bonded pair of electrons attached to an electronegative atom. So one of those electron hoggers, such as oxygen or nitrogen. This is going to act as your hydrogen bond acceptor. You're also going to have a hydrogen attached to an electronegative atom, such as an oxygen or nitrogen. And this hydrogen is going to be partly positive and it's going to act as your hydrogen donor. And as you'll see with water, you have them on the same molecule, but you can also have them on different molecules. And so water can form hydrogen bonds to itself, and it can also form hydrogen bonds to other things, and other things can form hydrogen bonds. So when we're talking about proteins, we see a lot of hydrogen bonding in the protein backbone, and this is responsible for like the secondary structure of proteins, so like alpha helices and beta strands and beta sheets. Hydrogen bonding is responsible for the complementary base pairing between DNA and RNA strands. But water can complicate everything because water can form hydrogen bonds with these things as well. And so it's always like a competition when things are in water to pair with one another rather than with water. And some water is very picky about what it wants to hang out with. So basically, because water has this polarity and it has this ability to form these hydrogen bonds, it's going to want to form these nice networks. So it forms these very happy water networks. And so in a liquid, what you have is basically these molecules are all like attracted to each other, but they're not all like ideally oriented in terms of that H-bond geometry. So as I mentioned before, these hydrogen bonds prefer to have like a specific geometry. In more detail, they like to have it where there's like it's linear between the donor, the hydrogen on the donor, and the lone pair. They need to like align for maximum strength. And so when we looked at the ice, it was all like everything was nicely aligned, and so you have the maximal strength. In a liquid, you kind of have the molecules, they have more energy, they're kind of moving around more, so they're not staying in that perfect alignment. And so these bonds are going to be like weaker. So the water molecules can like slip past one another and they can form hydrogen bonds with one molecule and then another and then another and then another. So everything's kind of like more like loose and moving around. So things can slip in there, but water is not going to want things to slip in there unless those things have something to offer the water. So if they have something that could hydrogen bond, or if they have some like other partial charge or full charge, then the water will let them into their network. And so basically we call things that water likes hydrophilic, and these can incorporate into the water network and all is good. But if you stick in something that's hydrophobic, something that doesn't have any partial charge, such as like a non-polar molecule, such as like a hydrocarbon, so something with just like hydrogens and carbons, if molecules share electrons fairly, then you're not going to get any like separation of charge, and so you're not going to get that polarity. You're not going to have a partial charge that the water likes. And we call these things hydrophobic. Water doesn't like hydrophobic things because it has nothing to offer the water. And so basically the water molecules are going to want to hang out with one another. And so they're going to kind of like cinch around these hydrophobic things. So the water is going to be trying to maximize its water-water interactions. And this is going to drive the hydrophobic things in together. And this is called like the hydrophobic effect. It's a main force in like protein folding because some of the protein letters, so some of the amino acids are very hydrophobic. And so when the protein is getting made and you have this chain of amino acids coming out of the ribosome, some of those amino acids, the hydrophobic ones, they're going to start like getting cinched together, and this is going to help drive protein folding. And so when you have a folded up protein, you end up typically with the hydrophobic residues like in the inside of the protein and the hydrophilic ones on the outside. So when you have these hydrophobic molecules together, they can still, you can get these like you can get like attractions between the hydrophobic molecules. But these are really weak, individually weak. They can be stronger together, but so typically we think about like attractions as happening between like charges or partial charges. But you can get like random partial charges. So basically if because those electrons are like moving all around, if they just like randomly happen to be like more on one side than the other, they can like induce a dipole. So they can induce like a partial charge in a neighboring molecule. And so basically you can think about if you have a bunch of electrons over here, and then there's a bunch of electrons over here in this molecule, these electrons are going to get repelled to the like the other side of the electron cloud or whatever. And so you can get this shifting and you can get this like chain effect. And so you can have these interactions between, you can have these like attractions between these hydrophobic molecules that are all huddled together. We often call these types of like instantaneous charge attraction type of things like van der Waals forces or London dispersion forces. And they're individually weak but collectively strong. And so they can help with explaining why the hydrophobic molecules like to be together. And what you'll actually have this a reason why they like get driven together, however, is that basically the water, because the water wants to exclude them. And so when the water excludes these molecules, it's entropically beneficial. And so entropy is a measure of like randomness or disorder, or the number of different like states a thing can be in. And so basically, if you have two hydrophobic molecules and they're separated, the water is going to cinch around the molecules. When water cinches around like hydrophobic molecules in these like tight shells, we call these clathrates. And basically this is taking all of these, it's taking a lot of water molecules around to like surround each of these molecules. And if you put those hydrophobic things together, now you don't need as many water molecules to surround them, because you can surround them all together instead of having to surround them separately. So this matters because now you see that here you had this like, you had to use all these water molecules, and when you're using these water molecules, they're kind of like stuck in these clathrates. So they don't have a lot of entropy or disorder. And entropy is like favorable, like thermodynamically favorable, basically. So it can be like a driving force for things binding, for reactions happening, all sorts of things. More on this in a minute. But basically, these can't be moving about randomly. So you have low entropy. There's a high entropy cost for this. But you can minimize the entropy cost by clumping together the hydrophobic things. And so when you clump together the hydrophobic things, now you have these small water molecules that are not out of commission. You can still use these water molecules, and these water molecules can be moving all around. And so you get high entropy. And so by forcing these hydrophobic things together, you're getting this entropic benefit. And this can be a big boost to help give you the energy you need in order to make reactions happen and in order to make things bind. So when we talk about whether a reaction will happen, it has to do with like a change in free energy. You can think about this as having high potential energy, and this is having low potential energy. It would take energy in order to push the ball up the hill, but you get energy when the ball rolls down the hill. And so the same idea with chemical potential energy. And so you had like a high energy reactants and you had low energy products. It would be favorable to go in the forward direction to turn your reactants into products. It would be harder to turn your products into reactants. So the difference in the energy is going to depend on these terms called enthalpy, temperature, and entropy. And so entropy, as we talked about, is that measure of like randomness or disorder. And so the more entropy, the more entropy the products have, the more favorable the energy, the more favorable the reaction. And enthalpy refers to changes in bonding. Often, of course, actually, there's like a barrier. Even if there's a higher energy of the reactants and a lower energy of the products, you have to pass this activation barrier where you have to add energy. And we have things called enzymes. So these like typically proteins, sometimes proteins and RNA, sometimes just RNA, that can help make it easier to reach they lower the activation barrier that's required in order to get the reaction to happen. Basically, if the bonds are in your products are more stable than the bonds in the reactants, then it'll be enthalpically favorable. But we don't really need to worry about this. right now. So basically, we want to worry about the entropy, and the entropy is going to play a huge role in biochemistry. And so if you take like organic chemistry and stuff, you often, a lot of times you basically ignore the entropy and you focus on the enthalpy. One of the reasons why is that the entropy is can be very hard to study, and it's dependent on solvents and all these various things. But we think a lot about entropy in biochemistry because of the water and the effects of binding on like desolvating the effects of like the water and the entropy benefit you get from freeing ordered water. So a lot of times, like drug compounds tend to be, they're often very hydrophobic. And so this can be a problem when drug manufacturers try to get these drugs like to be like water soluble and stuff, so that they can be used in people. One of the reasons why they're chosen is because, well, they often bind really well. And when they bind well, you're getting these favorable interactions, and typically these hydrophobic molecules are binding to like these hydrophobic drugs are binding to hydrophobic pockets and molecules and that sort of thing. And when they do that, they're freeing up all of that water that had to be used up in order to be ordering around like in that pocket and stuff. And so you're getting this entropic benefit by freeing up the water. And so it's a favorable, you get this energy gain from the binding. And so often it can get kind of confusing when you're thinking about entropy, like you're saying, like, so you get two things to bind and you're gaining entropy, that's entropy. How is that favorable? You would think that if you were getting two things to bind, you'd be decreasing entropy because you'd be sticking them together. They can't move around as much. But you have to consider the water. And so the water molecules that you're freeing, and remember the water molecules are probably like way smaller than your thing. And so there's going to be a lot more water molecules. You're going to have a lot more things freed than you have from the binding. And so this binding interaction can be favorable. But then you have the problem of trying to get it into cells. And so that's a big drug delivery is like a big hurdle for a lot of drug development. Enzymes lower the activation barrier that's required in order to get the reaction to happen. One of the ways that they do this is by actually providing, you get like binding energy. And so basically when these molecules are binding, often what they're doing is they're actually freeing a bunch of water molecules. And from like clock rate type things, so like from the ordered water molecules, they're freeing them to and getting that entropic benefit, getting that energy gain in order to help make the reaction more favorable, to make the reaction more cozy. Because water combines so many different things, it can often like hide things. And so you can get this like solvation layer where there's like water kind of like hanging out around something, but it's then hiding that thing from other things so that that other thing can't see that thing. And so for example, with if say you want two molecules to react with one another, well, they might not really be able to see one another because there's so much water surrounding both of them. So one of the ways that enzymes can work, so enzymes can work in all sorts of different ways, but one of the ways that they can work is that they can basically remove the solvation shell. So you can have interactions, the enzymes kind of like remove the water coat, but keeping the substrate soluble by replacing the bonds of water with bonds to the enzyme. And then when the enzyme like brings together these different things, they can see each other better because there's not all that water around. We can use a similar type of thinking in like when we're doing a DNA precipitation. And so basically the DNA, the backbone of the DNA, so typically it's actually coordinated through a kind of like magnesium, but basically you have this solvent layer along the DNA because the DNA's backbone has these negative charges from the phosphates. And so the water is going to be surrounding it. This is going to keep the water soluble. When you want to precipitate it, so you want it to make it unsoluble, such as when you're doing like some sort of experiment, you're doing a DNA extraction in the lab. Basically what you can do is you can add alcohol. What alcohol is going to do is it lowers the dielectric constant. So it's basically kind of, you can think of it as kind of using up some of the water, providing more non-polar stuff in there. And so this is going to allow, when you have a high salt, this is going to allow that high salt to bind to and neutralize the backbone, making it non-water soluble, because now it doesn't have anything to offer the water, and so the water is going to precipitate out, or it's going to and it could bind to like some membrane if you're doing like some sort of mini prep or that sort of thing, or if you're just doing it for fun, like a fruit extraction, then you can see the DNA. One final note is that water can basically auto-ionizes. And so basically this is the idea that you can have water and it can act as an acid and it can act as a base. And you can have water kind of break down to a hydroxide ion, so an OH minus, and a proton or H plus. But in reality, remember that we have so much more of this water. We have this like 55.5 molar of water. And so basically all of those protons, these protons are not just going to be freely floating around. Instead, what they're going to do is they're going to latch on to a water molecule to form this hydronium ion, or this H3O plus. And so there is only about, if we do some calculations, there's basically barely any ions in neutral water. So there's about 18 and 10 billion molecules. About 2 in a billion molecules of neutral water are ionized at any point. But we have so many billions and billions of water molecules that there's always going to be some of them around. And this ionization and proton swapping happens really, really fast. And so it's important. So you don't want to just like use like just H plus. Like a lot of times when you're taking like a biochemistry course or something, you'll see like H plus. I know I'm guilty of it too. In like equations or in diagrams, they'll just be like a random H plus. And note that H plus isn't really just hanging out. And so sometimes we don't know where a proton is going to come from. So we can draw this like generic acid HA and then use like have the proton be taken from that, instead of just drawing a free floating proton. And this leads to another thing. So proton transfer, so like moving a proton, so moving an H plus from one thing to another. It's a big aspect in both like biochemical reactions and organic reactions. So speaking of organic chemistry, I've been watching a lot of like YouTube videos because I really love organic chemistry and I didn't take enough of it. And so I'm just trying to like soak up as much as I can. And I've been watching like Chem 201 and Chem 202, which is like organic reaction mechanisms from UCI. Dr. David Franken. And so these videos are really helpful. And he talks about, so here there's a video where he's talking about how H is always attached to something. And here he's talking about proton transfers. And I found this video was really, really interesting. It's more like advanced. So if you don't want to get really confused, then don't watch this. If you want to get a little confused but make you think, this is a really good. And basically there's like proton transfers are actually going to go through, they start with like a hydrogen bond. And because we have the hydrogen bonds, because the hydrogen bonding is going to require that specific geometry, this is going to help explain how why you need to have like an intermediate when you're doing a proton transfer. Like you're not just going to have the transfer happen from like in like these weird angles where basically you often see this happen, like shown in diagrams, where basically you have this like intramolecular proton transfer at these like super weird angles, and you're like, yeah, it's not going to happen, because it has, instead you can draw it going through like a generic acid or base, so that you can get those these angles. Those angles correct, and these proton transfers are happening, they happen really, really fast, because the bonds are, the hydrogen to bonds, the bonds to hydrogen are wiggling really, really fast, and so they can break more easily, and so these are a lot faster than the other types of reactions, and a lot faster than trying to do some weird thing at this awkward angle. So this is a really, really fascinating video. Another one talking about kind of like thinking about the entropy, is this Intro to Chemical Biology by Gregory Weiss. And so yeah, I like this video as well. Yeah, so, and I highly recommend this, like these videos. Now I'm on 202. Still really, really interesting. And I'm hoping that in my postdoc, I'm going to get to do more like chemical biology. And so I'll be doing more of the chemistry type stuff. And so I want to get caught up. And also I just find this stuff really interesting. I think it's really interesting, kind of like revisiting things that you learned about a really long time ago. So when I was watching just like some of the OChem stuff, I learned, but now I have this biochemistry perspective that makes things helps me understand both biochemistry better and organic chemistry better. And a lot of this stuff is like brand new to me. But even though I haven't taken organic chemistry in a long time, by studying like biochemistry and by thinking about molecules all the time, things are really starting to make more sense. And it's also helping deepening my understanding of biochemistry. And so that's my little plug for the coolness of chemistry, and why, even though a lot of the things that you talk about in organic chemistry are kind of like they don't want things to be no water, by understanding these various things, by understanding what water can do, by understanding the makeup of all these molecules, you can better understand biochemistry, chemistry, organic chemistry, physics. There's so much you can learn just by thinking about what's happening in a molecule and between molecules. And yeah, so here's my plug to try to think like a molecule.